Okay, so question 65, draw the most stable conformer of the following molecule. So there are a couple of things for this molecule. The way that your book has it drawn is, or the cyclohexane ring, the way that it has it drawn is in this very overhead-like view. So, you have 1, 2, 3, 4, 5, 6 carbons here, and the way that it looks like it's planar. But what the way that we've talked about cyclohexane, what you know from class, what you know from your book, you know that that's not actually the case. You know that cyclohexane isn't actually planar, it's actually sitting in this chair conformation, it's puckered. So there are a few things to remember, and that's basically the main bit that you have to remember is what this wedge means and what this dash means. So what we've said is that this wedge is the way that you can interpret it, the way you can think about it in your head is either to think of the wedge as up or out of the page, or you can think of the dash as down or into the page, going into the other room, going behind the computer screen. So the way we can approach this is just go ahead and number the cyclohexane. So 1, 2, 3, 4, 5. And then 6. And then all we have to do is figure out where we want to put our methyl groups, because that's all we really have to deal with. So if we approach this problem from an up and a down motif, from what we've been talking about in terms of cis and trans, is that if you have one group pointing up and one group pointing down, no matter what it is, whether it's axial or equatorial, then you have to have a trans configuration. So that's what we want to end up drawing, is a trans configuration between 1 and 3 and between 1 and 5. Between 5 and 3, both of these are going to be pointing down, so you'll want 3 and 5 to be both pointing in the same direction, so those will be cis. But let's just go ahead and start counting from carbon 1. So carbon 1, I'll go ahead and redraw that on the inside actually. 1, 2, 3, 4, 5. Okay, so I'll go ahead and arbitrarily assign 1 as pointing up. Okay, so that'll be my methyl group. And then on carbon 3 right here, we'll have the methyl group pointing down. So the only way it can be pointing down is if we have an equatorial position, so that's our methyl. For 5 is also pointing down, and the only available down position here is equatorial. Okay, so that has to be this methyl group right here. Okay, so that's one possibility. We could have started off with the other possibility of, the methyl group on 1 pointing, down. Well, actually, the way that we've gone about that, let's not say that. Let's go ahead and get rid of this guy. So I'll get rid of it. And instead of reorienting our eyeball, let's go ahead and say that we're going to do a ring flip. So let's do a ring flip real quick. So we'll do a ring flip. And this will be our ring flip. So go ahead and redraw this cyclohexane ring. Pause the video, redraw the cyclohexane ring, and try to draw it after the ring flip and reposition all of these methyl groups. Okay, so go ahead and pause the video, come back in a sec. Okay, so I've redrawn my cyclohexane ring. It looks a little funky, but it's usable, so we'll go ahead and go with that. So if this initial carbon 1 is pointing up, again, we know it's pointing up like this. This carbon 1 must, after the ring flip, be pointing down. So again, let's just make this carbon 1 since it's pointing down. So now if the methyl is pointing up axial, after we do the flip, it has to be pointing up equatorial. So that's our methyl, and axial down will be just a hydrogen. So if we go around the ring in a clockwise fashion, so if we're looking down this way with our little eyeball, so we're looking down, everything's going in a clockwise fashion. So this is 1, 2, 3, 4, and 5 right here. So that'll be 5. Okay, so now we have to figure out what to do with carbon 3. So this methyl group is still pointing down axial. So after we do the ring flip, it's still going to be pointing down, but now it's going to be equatorial. So this is 3, and this is going to be pointing down axial. And so that's our methyl group right there. We'll have an equatorial up hydrogen. And if we look at carbon 5, the methyl group on carbon 5 before the ring flip was pointing down equatorial. So after the ring flip, it must still be pointing down, but now it must be axial. So here's our methyl group pointing down, and it is axial. And if we want to draw another hydrogen, we can try to draw one. It's a little hard because my cyclohexane looks a little funky, but this is a equatorial up hydrogen. It's not completely vertical, so this would go by as equatorial. Okay, so now The question is, draw the most stable conformer of the following molecule. So again, this is just going back to stability of equatorial versus axial. Unfortunately, in this case, we're never going to be able to have the molecule with all of the methyl groups in an equatorial position. So we can't have our cake and eat it too. We'll have to basically figure out the most stable conformer that we can get. Okay, so in the first example, we have 2 equatorial groups and 1 axial. And in the second example, in the second conformer, after we do the ring flip, we have 2 axials and 1 equatorial. So in this case, we have one relatively stable configuration, and in this case, we have 2 stable configurations. So between the two, this is the most stable conformer, and this one on the right is going to be the least stable. Okay? And that's actually all there is to this question. Okay? Next question.